Well, thank you very much, Liang. You were talking about me. Okay, well. Um, anyway, I'm sneaking away from NCAR to do some science, and it's been great to talk with all the faculty and students and postdocs. It's just very exciting. And I'm really honored to be invited to speak at this DeFord lecture. So I didn't realize that it's a big deal. And it is a big deal, it's great, and I get to share some science with you. So I promise I won't talk budgets or any of the other things that I know my NCAR folks would be expecting. I'm talking about some science, some land-atmosphere interaction. So let's see, I think this will work here. Since it's a very oblique angle, I'll probably speak to this so I can look at you, but you can see the big picture. So, local land-atmosphere coupling and interaction. Will clouds form? I like this photo, one of many. It's nice because it shows the land surface and it shows, well, clouds that form through that interaction. And you can see the shadows there too. So there's a definitely connection with the, the land atmosphere coupling, radiation budget, which in turn affects the land processes, and that's all interacting. So we'll keep talking about that. Just so you know where I'm from, this wasn't a recent picture, but I will say 2 weeks ago we had 3 inches of snow in Boulder. So I'm very much enjoying the warmer weather, and I guess I don't want to get here too much later in the year, but it's been very nice and pleasant, nice breezes, and talk with everybody outside. But this is kind of a common feature. I'll say this is the NCAR Mesa Lab, which a lot of people think of when they think of going to NCAR in Boulder. So it's the more I'll say it. It's the more cool looking lab, definitely. And that's where, if you haven't visited, it's really good. And there's a noted architect, I.M. Pei, who designed this building in the 60s. So important to see. I'll share this because I had an honor to be with Liang when he got his AMS fellow at the meeting in New Orleans in 2025, and then there was a celebration at Antoine's, the home of Oysters Rockefeller. But we got there in time to actually be part of a historic southern Louisiana snowstorm, and you can see from this picture here that it extended from, this part of Texas over all through the south and into these states. And it was interesting because my daughter lives right here, my son lives right here, and my other daughter is right here. So they all got snow when other parts of the country were not. So it was just amazing to get 7 inches of snow in Lafayette. Their average snowfall for this time of year is 0. And that's a pretty routine climatology. But my granddaughters absolutely loved the snow. And so every time they visit in Colorado has always been in January, and they always assume there's always snow here, Papa, isn't there? But anyway, they got to show me their snow, which was really incredible. So I just thought I'd share this part here. So what is the role of land in Earth system predictability for weather and climate? You all have probably seen this picture at one time or another. It comes from Paul Dermeyer, George Mason University. He's a close colleague of ours who we've been working with for years. It just shows the time scales of how things are connected. The atmosphere is on a very short time scale. So in other words, the memory is shorter in the atmosphere. It's stronger in the land as you get out to some beyond 7 days, say multiple weeks and so on. And then of course the ocean has very long time scales, more of a climate. And it's important that the land states like soil moisture, snow, and soil temperature, they provide the predictability for deterministic weather from day 0, like in NWP models, all the way out to climate, but they peak at the seasonal time scale. So land has that role. Vegetation states, basically a function of soil moisture anomalies, are also important in terms of memory for the land. Land-atmosphere coupling is active where there is sensitivity, variability, and memory. That's really important for us to understand. My NCAR colleagues don't like me to say it, but I think the atmosphere is just a very well-mixed boundary condition for land and ice and snow. And the ocean, we'll throw that in there as well. And good models and analyses of the atmosphere and the land states are really needed to exploit this skill. So I'm giving you the big background picture. We can move to one more background picture, of course. Land is important for the atmospheric energy and water budgets, the water cycle. So you need to properly represent and close the energy budget and the water budgets, the hydrological cycle, to provide these surface boundary conditions in weather and climate models. And as they expand and they're more fully coupled Earth system models, all this needs to be represented properly. So definitely all the land-related efforts in here. So for the both energy and water budgets, once you start moving into the climate time scales, then you also have to worry about biogeochemical cycles such as carbon, and these are particularly important for climate models. So really careful bookkeeping is required. So let's go into land-atmosphere interactions. So the land and atmosphere are intimately coupled, the short to the long time scales. It's a very intimate dance in nature. However, historically, land models and atmospheric models have been developed separately, and then they're plugged together, and this is not really so good for developing, simulating coupled land-atmosphere processes. So, the land-atmosphere interactions still remain a weak link in Earth system models for both weather and climate. The coupling strength, like the surface fluxes and the affected boundary layer evolution, and whatever the downstream influences are from that, those things need to be properly represented. It's important for weather and climate. So we need to use and develop land-atmosphere coupling metrics. Is the coupling correct in your model? Are you getting the right land-atmosphere coupling? And there's many, many different land processes, land and atmospheric processes, interactions, and we have to represent them properly in our weather and climate models. And for example, the soil moisture and the evaporative flux to the atmosphere, the boundary layer development, clouds, convection, hydrology, river flow, connections to ocean, dust suspension, surface chemistry, interactions with plants, etc. So there's many, many, many things going on. We do remember that coupling begins locally. Your teleconnections don't work unless all those physical processes are working. So let's move on. Let's look at this coupling. Well, this comes from GWEX. I'll talk about that a little bit later, but Global Energy and Water Exchanges Program. There's a local land-atmosphere coupling project where we're trying to look at these processes with changing soil moisture, changing temperature, moisture, changing evaporative flux, the boundary layer development, clouds, entrainment, etc. All those things are working together. The land-atmosphere coupling really stands on two legs. There is feedback paths. So there's a terrestrial leg where the soil moisture changes, and that affects the moisture fluxes. The fluxes change, which affect the boundary layer development, and of course the changing precipitation kind of acts to change the soil moisture, changes the fluxes, changes the boundary layer development, changes clouds and precip, and such that all of those are interacting. So there's the terrestrial leg. So the questions for that is when and where does the soil moisture, vegetation, soil, snow, where does it control the partitioning of the net radiation into sensible and latent heat flux and soil heat flux? So what you're seeing in this part of the cycle is the changing soil moisture changes changes ET, evapotranspiration, and sensible heat flux. So in an arid environment that with soil moisture low, and then in the humid environment, you're getting more sensible latent heat flux and evapotranspiration. On the other side, the atmospheric leg is where and when and where do the surface fluxes significantly affect boundary layer growth, clouds, precipitation, etc. And so in arid regions with low ET, as you get to more humid regions, you're more in strong precipitation environment, and similarly, the sensible heat flux affects boundary layer growth, so very different in an arid environment where there's stronger boundary layer growth than in a humid environment because more energy is going into evaporation and less into the boundary layer growth. So many, many processes that are going on here, and this is a simple representation of it. So if we look, what is really under the hood? What do we need to understand? The question is, will clouds form? Well, there's basically all these interactions going on. A friend at NASA likes to use this figure of mine because he uses it for kind of the shock value in program managers when he's trying to say, this is what we need to represent. So it's necessary to understand all these processes to actually improve our models, and that's whether it's short, medium range, long-term timescale, subseasonal, seasonal timescales as well. And we need to get all of these processes right and their interactions for the right reasons in our weather and climate models. So all these things are going on. It's interesting because this was a challenge from my PhD advisor years ago. He said, what are the interactions that we have in this simple land boundary layer radiation model? And these are those interactions that are going on. So let's talk about this a little more. So you look at all of these processes, and you actually have a radiation budget. So let's just look at the feedback cycles here. Let's do this. Okay. So if you increase the incoming solar radiation, that increases the emitted long wave, which affects the surface temperature, which actually will affect the downward radiation. But similarly, if the cloud cover, for whatever reason, increases, you'll decrease the incoming solar, but you can see the other interactions that are going on. Actually, with increased cloud cover, there's more downward long wave. The downward long wave affects the surface moisture flux, and of course that interacts then increasing the relative humidity. All of these things are going on. And this is from the radiation standpoint. So positive feedback means if it's a solid line, you increase one thing, you increase the other. If it's a dashed line, you increase one, you decrease the other. So it's being able to understand each of these processes and making sure that you're representing them correctly. And then there's some details on interaction with various kind of plants. So on the other hand, let's see, here is looking at the atmospheric turbulence quantities. So increasing the temperature increases the boundary layer. Increasing the temperature. I was pointing at the screen here earlier. How could you see that? You increase the surface sensible heat flux for whatever reason. That increases the boundary layer growth, which increases the entrainment, which increases the temperature, which increases the potential temperature, but the entrainment lowers the humidity. And so you have things that are battling each other. You increase the sensible heat flux, you increase the temperature, but then that decreases the humidity at the top of the growing boundary layer. All of these things interacting then to form clouds or not. And then you have some background things going on. What is the dryness above the atmospheric boundary layer? What is the stability? And those things are affecting each other. So, let's see, here we go. No. Oops. All right, there we go. So then there's the surface processes, land processes. If you increase the soil moisture, you increase the moisture flux. And when you increase the moisture flux, you increase the soil heat flux because of the stronger conductivity, but that actually decreases the moisture flux through a negative feedback here. You increase the moisture flux, the soil heat flux, that increases the soil temperature, but then you increase the soil temperature, then that decreases the soil heat flux because then the gradient is decreased. So there's a lot of, So there's a lot of interactions going on, and all of these things simultaneously we need to get right. And I will contend that some people may spend their entire PhD working on a particular arrow or set of arrows. So there's a lot of things to understand with this. So there's some equations to explore this, and that's what we're using to talk about today. Equations for the surface energy budget, what's transpiration, canopy conductance, surface turbulent exchange, direct evaporation, what is the boundary layer growth, what is the boundary layer top entrainment. These are processes that are going on, and those are occurring with all of these processes going on in the background. So, am I going forward? Yes. So let's look at the terrestrial leg, which we talked about just a moment ago. So just kind of focusing on this bottom part here. So what is the nature of the near surface local land atmospheric interactions that are going on? So for strong coupling, a strong connection, a strong coupling for a given soil moisture change that yields a large evapotranspiration change. If it's weak coupling, then the soil moisture change is small for a given evapotranspiration change. So the question is, what is the relationship between the soil moisture and the evapotranspiration, or the evaporative fraction, you could say, in terms of the near surface turbulence, the atmospheric variables, and vegetation and soil processes? Again, we're taking a subset of all these arrows to try to understand the terrestrial leg, so this right here. This is an extension of work by Jarvis 85 and Koryakobs and company in 2008, actually using the European Center model. And let's just focus on this near surface and vegetative processes and the role of soil moisture. So here's some equations that we'll put together here. This is Penman-Monteith relationship for evapotranspiration, but basically we've converted it into an evaporative fraction simply by dividing by net radiation minus G. And you basically get this representation to describe what is this relationship, and we want to know how does the evaporative fraction change with changing soil moisture. So it's a different, you differentiate this, and what you have is some terms having to do with the available root zone soil moisture. These are constants depending on what's going on in the atmosphere. But the big things here are the canopy conductance, which is the effect of plants and transpiration. This is the aerodynamic conductance, the inverse of that, and essentially the turbulence. But what's interesting, what falls out of this is, and then it neglects the soil heat flux effects, which are smaller, and the non-vegetative case, so for the bare soil, but we'll just focus on the vegetative case here. But what this basically collapses to is what I call, or what somebody called for me, and now I've adopted it, little omega. So essentially, if you just look at this equation right here, this is really bounded by simply, for really, really strong coupling, this value tends towards 1. For very weak coupling, it tends towards 0. So where do you see this? Real strong coupling. So you change the soil moisture, then you'll change the flux quite a bit. That might be for an area, for a vegetation that has strong stop model control and strong turbulence, such as a forest, with dry soil. On the other hand, for weaker coupling, you might expect that for a vegetation with weak stop model control and weaker turbulence, such as grassland or cropland over wet soil. So, over wet soil. So trying to contrast that, where is the connection and coupling strong, where is it weak? And so we wanted to explore this by looking at Ameriflux data, FluxNet process, and analyzing this little omega with using long record lengths and focus on the midday summertime. So I took a bunch of flux sites in different parts of the country to try to characterize this. Here's just a snapshot, here's just a picture of the terrain and the vegetation type. So we wanted to examine the change in evaporative fraction with the change in soil moisture versus the coupling strength. So that's to understand then the role of soil moisture, where it's strong or weak. And so we use the daily change because to get a signal to emerge, you really need to see what's going on one day to the next. And so we find that there was stronger coupling for forests and weaker couplings for grasslands, kind of as predicted. Let's see, moving over here. And so the Brookings is a grassland site, and the Black Hills is a forest site. And kind of simply, crudely looking at these data points, we don't see a lot of strong control in terms of this omega as you go from a low evaporative fraction to a high evaporative fraction. Although we do see this more in the forest. So as you go from low evaporative fraction to high evaporative fraction, you can see the coupling diminish. It's higher over the forest, and then as it gets wetter soils, then the coupling is diminished. So what does this say? Well, first of all, we really need to examine additional FluxNet data sets, especially looking at longer time scales. The dry down over the course of weeks, days and weeks is really important to address. So this is just sort of an initial examination of some of the FluxNet data, but there's an awful lot in the US and around the world to be able to allow us to look at that. We also need to include the bare soil case because that's some different properties that are showing up because vegetation is involved with that. It's more what are the soil properties and this little bit minor soil heat flux effect on what we get for our strength of coupling. So mentioning this terrestrial leg, it's part of properly representing the land atmosphere, forgot the A, interactions in our models. So you need to have this properly represented, and so this terrestrial leg is just one part of the total picture. So let's go back to our equations to explore this again, where we're looking at surface energy, budget, transpiration, et cetera, boundary layer growth, boundary layer top, dry air entrainment. So looking at this atmospheric leg, basically, how does the land surface impact the onset of cumulus? Okay. What is the role of soil moisture in the atmospheric processes in doing this? And how do you quantify this? Relative humidity tendency is a nice quantity to look at because it's expected to control the cloud initiation. Typically, the higher, some microphysics effects aside, typically if you increase the boundary layer top relative humidity, you're expected to get more cloud initiation. So you can look at the relative humidity derivation with time here. It's just basically all of these terms right here having to do with the change in, this is the specific humidity, this is the saturation specific humidity. So the change in moisture through time, the change in saturated moisture through time, and this comes out to these quantities here, relative humidity factors in, ultimately end up with this equation here. But there's it's nice when you plug in those equations that I previously mentioned, it kind of collapses nicely into this representation. So the role of evaporation in boundary layer development and cloud initiation, we're talking to fair weather cumulus, not like severe convection or anything like that. So basically it collapses to this equation right here. So that previous page, this last equation, when you plug in all of these things, is basically the net radiation minus soil heat flux. This is just air density. This is latent heat of fusion, boundary layer top, and the temperature, well, the specific saturation specific humidity at the top of the boundary layer, and that's just a function of temperature. And then basically it's this term times the evaporative fraction plus its non-evaporative terms times 1 minus EF. Oh, okay. Well, that seems simple enough. What does that look like? It looks like this. So this is normalized. Oh, let's see. Did I go here? Okay. So this is normalized. So essentially, this phase diagram is just EF plus NE times 1 minus EF. So this term is an available energy term, and this is always positive as long as your net radiation is greater than your soil heat flux. And that's typical daytime conditions. But what's going on with this EF plus NE times 1 minus EF? We'll call this the normalized tendency equation. So that's what this phase diagram shows. So, and what is this NE thing? Okay, well that falls out, and it's basically these terms here. Well, what are these really? Well, this is the dry air entrainment term, and it has a negative contribution to the humidity tendency. So remember, if this if this humidity is increasing with time at the top of the growing boundary layer, you can expect to get clouds. Maybe, if you start out with a high enough relative humidity. But the thing is, the stronger the entrainment is, then that's going to be a negative contribution. But then there's also a boundary layer growth term, so that's positive. So the more boundary layer growth, the more the more the humidity is going to drop at the top of the growing boundary layer. And then there's a boundary layer warming term, actually, which is a negative contribution. It's bringing in dry air, it's bringing warming into the boundary layer, so that actually then decreases the humidity tendency. So the interesting thing is, if you look at it in this normalized tendency, in a surface moistening regime, so these non-evaporative terms right here, are acting such that they're either in this domain where this normalized tendency is pretty negative for the most part, but then there's some slight positives. But we call this the surface moistening regime. So you have basically stronger above the boundary layer stability and or really large dry air entrainment. So basically what this says is that your relative humidity tendency, your tendency for this to be positive, is increasing when you increase the evaporative fraction. So more moisture, surface moisture, but evaporative fraction. However, in the boundary layer growth regime, typically you'll find this if you have weaker above atmospheric, above ABL stability. So it's a weak capping inversion, or the delta Q is small. In other words, it's not really dry above the boundary layer. So in this case, actually, in this phase diagram, your humidity tendency increases as you decrease the evaporative fraction. So what's going on here? It just says that your greatest relative humidity tendency and potential for boundary layer cloud initiation is going to be as long as we're up above this NE equals 1 line, our biggest potential for our H tendency increase is sitting in this region right here. So you're over drier soils, but your boundary layer can grow unrestricted. So your RH tendency is larger up, up in this region, this phase diagram. So, there's just a subtlety between the boundary layer growing, the temperature drops at the top of the growing boundary layer, and so your relative humidity goes up. But the greater the boundary layer growth, the more entrainment of dry air you have. So the entrainment of dry air acts the opposite way of that. So which one dominates? You can take this same diagram and you can actually look at when does that NE term fall above or below the 1 line. And typically if you get drier air aloft, then that means that sends you down into this regime, into the boundary layer moistening regime. So if this value of the dry air above the boundary layer is greater than some critical value, then you'll see who wins over boundary layer growth versus dry air entrainment. And this is just a way to quantify it. And you can just pull these out from observations and you can see when does boundary layer growth win over when does boundary layer dry air entrainment win. So again, those are two opposing forces. So let's explore this with a single column model doing some sensitivity tests. What is the role of soil moisture? Vary the soil moisture from very dry to very wet. So here's very dry on one side, here's very wet in the middle. Vary the inversion strength from very strong to very weak. So very strong holds the boundary layer from growing. Very weak just lets it grow unrestricted. Vary the boundary layer air above it to be from dry to say not so dry. And then other tests, you could do are different vegetation and soil types, background advection, different regions, etc. But just focusing on these three in terms of the sensitivity testing. I used a single column model with an interactive land surface and clouds and a simple radiation scheme. This actually comes from the original land model that became NOAA MP, and it came from the original model that is now in the YSU PBL scheme in the WRF model, and then a simple PDF-based boundary layer scheme. So these tests using the boundary layer, using this simple model, were very interesting. We have a single column model, again, with this interactive land surface, PBL, and radiation. And so are we going to, where do we get farewell the cumulus forming? I just used a data set from the Netherlands kind of as a benchmark to look at these sensitivity tests. So what is this? Well, this is varying soil moisture from very wet no particular index, just from very dry to very wet. Okay, and then we're varying, very dry to very wet. We're varying the inversion strength from very strong to very weak. Okay, these two different sides. So what do we get here? Also the air above the boundary layer is actually less than this critical value, such that it's not terribly big, so the drying from the entrainment of dry air above the boundary layer is not going to be nearly as important. So what happens? Okay, here's the cloud cover we get from these different interactions. So what are going on with these two different kind of tests? Well, if you look at this test right here, okay, we have a very dry soil with a very strong inversion. So you get a shallow boundary layer. It just doesn't allow the boundary layer to grow very deep, so you don't get clouds forming. Okay. For a very dry soil but a weak inversion, so very dry soil but a weak inversion, that means the boundary layer grows just unrestricted. So wait a minute, you get a lot more clouds over dry soil in this case. Boy, what's going on? Well, all those interacting processes, some non-intuitive. So with a moist soil, you get a very shallow boundary layer. The cloud cover is kind of similar regardless of the inversion strength, because most of the energy then is going into the latent heat flux, and that allows boundary layer growth, but it's rather anemic. It doesn't grow terribly big. Over here, very dry, but there's a strong capping inversion. In this case, weak capping inversion, it can just grow unrestricted. So you can do another set of tests. Let's make this delta Q really large. It's really dry above the boundary layer. So that means our delta Q is greater than some critical value. So basically it's going to say that the entrainment drying wins out over the boundary layer growth. And so when you have dry aloft, when it's dry aloft and you have a delta Q very large, you get fewer clouds forming regardless of the inversion strength. So the dry air wins in this case. So this is a set of sensitivity tests that just basically illustrates when and how you get these things happening. So it's kind of interesting to look and go, wait a minute, more clouds over dry soil? What is going on here? Well, there's a number of interactions that are going on. You certainly have to have a high enough relative humidity in the first place. It can't be completely dry in the boundary layer. But if it's near a threshold, or if it's at least it's a certain value so that the relative humidity can increase as your boundary layer growth increases, then you will get then more clouds over the drier soils. So I skipped a bunch of slides here because I was looking at different field programs and basically what the results showed over in the Sahel, in place in central France, field program actually in the Netherlands as well. But I just summarized it using this, non-colorful diagram, but just to show that the studies are such that in the Netherlands, I was just in this region. So you're in the boundary layer kind of moistening regime. When you looked in the Apex Mobley study in France, you were kind of straddling this 1.0 line, such that some of the studies suggested that, oh, well, wait a minute, when you have drier soils, you could actually get some more clouds forming. And actually, in an AMA study, which was West Africa, you were definitely all in this environment such that you wanted drier conditions for your boundary layer to grow because there was very dry soils, but the inversion was weak. So when do you get clouds forming? There's a lot of interactions that are going on, and this is just a way to quantify it. So if we notice in these different field programs here, the evaporative fraction is somewhat constant, while the NE term, non-evaporative terms, increases during the day. And how general is that? Well, that would be really good for us to find out. So basically, this was for just fair weather cumulus. Generally, there was less than 20% coverage, but you could have a lot bigger percentage as well. but without getting into like severe convection or something like that. We're just looking at fair weather cumulus, whether or not they form. So obviously, I need to look at a lot more data sets from many more field programs. This is a goal of mine that I might do, that I will do when I get time for science. And so essentially it says the atmospheric part of this leg is also part of properly representing land atmosphere processes and interactions in Earth system models. So you need to get the surface leg, or you need to get the terrestrial leg. What is the effect of soil moisture on the fluxes? And then you need to get the atmospheric leg correct, the effect of surface fluxes on the boundary layer evolution. So, actually, yeah, I grabbed this one. I did this about maybe 15 or 20 years ago. I just started writing it out, looking at those equations, and you can see drh dt, and I was very excitedly writing out how it looked, because I went, well, how do we quantify this? How do we see that, oh, wait a minute, you have drier soils and you get more relative humidity increase? And so it just mathematically fell out of this. And I think I mentioned this in my dissertation too. A woman was looking at me, writing just feverishly when I was on the plane, and she said, "What are you doing?" And I said, "I'm looking at the role of soil moisture in boundary layer cloud evolution, and I can see that you get more clouds over drier soils." And she said, "Okay." So anyway, sometimes these things sort of fall out, and I just happened to save this this diagram. So summary in future. So we've examined the role of soil moisture and soil and other states, land characteristics, et cetera, et cetera, et cetera. Surface fluxes, boundary layer processes. Basically, this increases our understanding of whether clouds will be initiated or not. How do we translate this information to weather and climate models? Well, I think it comes down to getting the processes right. Because the one thing you don't want to do is just play around with your model so much that you tune it and you lose the understanding of the physics that's really going on. So we need to understand these near surface as well as boundary layer interactions, land boundary layer interactions. We need to evaluate many more land atmosphere data sets. And as our weather and climate models move to fully coupled Earth system models for weather and climate, including hydrology, ecosystems, biogeochemical cycles, and everything, we have less degrees of freedom to play around. In other words, we don't have tuning knobs to accommodate our systematic biases. It boils down to we need to get the right answers for the right reasons. So, in other words, we need to properly represent all those land atmosphere processes, land atmosphere interaction and coupling, including clouds, a tall order. I'll just say the International World Climate Research Program, Global Energy and Water Exchanges, Global Land Atmosphere System Studies projects are examining this land atmosphere interaction. And basically, just to say where they fit, here's the WMO, there's the World Weather Research Program, which has a project on precipitation and hydrology, which very much affects land atmosphere interaction. And then on the World Climate Research Program side, there's the GWEX project, which actually has this sub-working group on global land atmosphere system studies, and definitely working on land models and understanding our land atmosphere interactions and what goes on there. So I'd like to close with, well, I guess you can still see it. Yeah, this is land and clouds and shadows and land atmosphere interaction processes. A lot of stuff is going on to represent all of these things and get this right, and here's the above boundary layer and so on. So we just have to remember that, yeah, thank you, and that all of this is going on to give you those clouds. So that's it.